Okay, let's look at another nice application of similar triangles here. Um, so this is a midline triangle theorem. So first of all, let's review a definition. A midline of a polygon is a line segment whose endpoints are midpoints of consecutive sides of the polygon. So a triangle will have three of those. So the midline triangle of a given triangle is the triangle consisting of the three midlines of the original triangle. Now, it's very important that you spend some time and do some investigation of this stuff on your own before you watch me do it and work out a proof here. So I'd really like you to do the following task on your own. So after we read through the task, I'd like you to stop the video, go do this task, see if you can do this work yourself, and then come back to the video and kind of pick up where you left off. So this is a midline triangle discovery task. In GeoGebra, construct a general triangle ABC, construct midpoints X, Y, and Z of the sides, construct a single hide show checkbox for the midpoints, construct triangle XYZ, which is made up of the three midlines, construct separate hide show checkboxes for each of the midlines. And then what relationship do you notice about these two triangles? Do you see any other triangles form? List as many relationships among the triangles as you can find and be as specific as possible. Okay, and of course test your conjectures out. Okay, so then you test your conjectures by performing some measurements and manipulated A, B, and C, and then prove your conjecture. Okay, and it does have something to do with one or more pairs of similar triangles. Okay, so see if you can do that on your own before you come back to the rest of the video. Just stop the video now, do that, and then come back. Press pause or stop now. Okay, so I hope you went back and actually did that construction and you found out from that the following theorem. Now, you're going to learn so much more if you do the construction yourself and you give the proof a shot yourself. Maybe you'll come up with a great proof and this will be just reinforcement, or maybe you got stuck somewhere, but then either way, you're going to learn from doing this work. So again, if you haven't done this work yourself, I encourage you to go back and do it. So assuming you've done that, given any triangle ABC, each midline is parallel to and half as long as a side of the triangle. Furthermore, the sides of the triangle and the midline triangle include three additional triangles congruent to the midline triangle. Each of these four triangles is similar to triangle ABC with proportionality constant 1/2. So here is a visual here, or dynamically we can look at here. So here we have a triangle. It's just a general triangle. I can make any triangle out of it. Let's say there, for example. And then I've got the midpoints here, which you can see. And then we can start by that. Let's show only one midline. Let's say this one. Okay. What does it look like is happening here? Well, first of all, it looks like what? Does it look like those are parallel? Yeah, they are there. What about the other one? Is that one parallel over here? What about this one? Yeah, that looks like it's parallel. How do the lengths relate? So let's look at the lengths of the sides versus the lengths of the midlines. Well, if you look, they're all half as big. So we see that the midlines appear to be parallel to the side and half as big. Okay, so let's see if we could maybe go about proving that somehow. Okay, so actually I think we've actually already proved this in an earlier video. So we did this in a video earlier, proposition 92 for my list It's a triangle midline theorem. And we already, if you can look that video back up a little bit earlier in the playlist, we already proved that each midline is parallel to and half as long as the side of the triangle. So by the side-side-side triangle similarity theorem, we have triangle XYZ is similar to triangle ABC with proportionality constant 1/2. And furthermore, we've already shown the same thing for each one of these, like this triangle up here. Oh, let's do the one down here first. YZ is similar to CB. Let's see, ABC is similar to AYZ. No, AZY, which is what we say here. And then we also have these other similar triangles. So the one up here, 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 all four of these we've shown are similar to this triangle here. And each of these little ones has proportionality constant 1/2. And so, well, that makes all of those four little triangles congruent by the side angle side postulate. They all have, we've already shown that they have all the angles, corresponding angles congruent. And now we know they all have a side of the same length as well. For example, since this is a midpoint, these two have a side that's the same length. These two hits a midpoint, so those two have a side the same length, and so forth for these two. And this green length here is the same as the length from A to Z here, and so forth. Okay? So that means all four of those triangles are similar to the big triangle, and the four little triangles are congruent. Now we're going to formally look at area in a couple of chapters, a couple of playlists down the way, but you're probably already familiar with the concept. So can you see that the area of the big triangle ABC is 4 times the area of each of these four little triangles? Or in other words, 4 times the area of the midline triangle. Okay? That is the midline triangle.